Szanowni Państwo, bardzo serdecznie witam w ten poniedziałkowy wieczór na Wydziale Fizyki. Nazywam się Krzysztof Turzyński, jestem prodziekanem tego Wydziału do Spraw Studenckich, a ponieważ językiem roboczym naszego spotkania jest język angielski, to chciałbym się teraz przełączyć na ten język i zacząć jeszcze raz od początku. Ladies and gentlemen, welcome tonight at the Faculty of Physics, and we are going to have a very interesting program for you. The event is a part of our greatest series, which is called Ask a Physicist. This is a series during which distinguished people from all avenues of science, mostly physics, but we also welcome a representative of other branches of science and also important administrators, come to the community of the Faculty of Physics and friends and address our most pressing questions. The organizer of the entire series is Professor Piotr Sułkowski, whom I would like to ask to introduce our distinguished guest tonight.
Thank you. So we are meeting again for this lecture. Our guest today is Aline de Cloizeaux. She is a director of the Division of Nuclear Power in International Atomic Energy Agency. This is this acronym IAEA you might have seen in the poster. So we are happy to have her here. Apart from being director, she also used to be a leader of Women in Nuclear organization in France. So this is one of important initiatives she has led. And the title of her lecture is Nuclear Power, Global Prospects and IAEA Support.
So, yes, it's working. So it's really an honor for me, ladies and gentlemen, to be here tonight with you and to present nuclear power, global prospect and IAEA support. But just to start with, a few words about my background. So I studied a long time ago mathematics, physics, and even civil engineering. And I joined the nuclear industry by chance, because I did some internship. I found that it was extremely good and complex environment that I liked it. So during my more than 30 years of experience, I did, in fact, a lot of projects, nuclear new build projects, as project director, but with a technical background, because I believe that it is a field where you have to mix different kind of competencies, good scientific and technical background first, but also project management, economics, and yes, a certain HR, management of big teams, HR, and so on. I joined the agency beginning of 2022. So I've been there for a little bit more than 2 years now. And it's really a good place to work with in very international environment. And it's a place where also I can promote what we are doing, not only in the agency, but also the benefits of nuclear power. And we can help countries, either operating countries or what we call newcomer countries like Poland, who are developing a nuclear power program, because it engaged a country for more than a century. And it needs competencies, development of competencies to support the program, from design, engineering, licensing, construction, but also after operation, and all the fuel cycle, waste management, and decommissioning and dismantling. And so that's why I asked if there was an opportunity. Oh, it's better, I think, the sound. To give a lecture, first to meet university and to give a lecture. And I am happy to learn that there will be a nuclear engineering course starting next year, because yes, it's important also, as I said, to prepare the young generation. and it should be done in international cooperation mode, as we promote it also in the agency. But to start with, so I will explain why nuclear power. Second, I will speak about nuclear technology innovation, what's in front of us, and at the last part, I will speak about what we do in IAEA to support this. And if I'm too long, I will try to also take care of the time, because it's already late in the evening. So first of all, why do we need nuclear power? And it's really related to something which is now pressing, which is energy access and climate change, first of all. And so first of all, why nuclear power? On this chart, and in the IAEA, we produce a lot of studies, and you can find this. But we also are working with the International Energy Agency, other international organization, who are looking at nuclear as part of the energy mix. So, but when we are looking at the life cycle greenhouse gas emissions of all the different nuclear, not nuclear, but power generation, we can see that nuclear is very well positioned between hydropower and wind power as one of the lowest GHG emission producer during all the life cycle. Of course, it's coal, biomass, natural gas, all this CO2 emission, I would say, source of energy are very big contributor to climate change, not only, of course, but they are big contributors. And really because we now have this race against climate change, it's not anymore a question, it's now a certainty that there is a global increase of temperature in the world. And now we have to really race to lower and to limit, in fact, the effect of this CO2 emission. And so there are many countries that have pledged for going to net zero by 2050, some a little bit later, but many countries have pledged against that. There are yearly COP. I think that you follow this quite carefully, and Poland has pledged for this, like many other European countries, by the way. So one of the topics to stop coal and gas power plants, and to stop emission not only by electricity production but by energy production, there is a need of clean energy production, and of course renewable will have their place, will be have a growing place. Wind and solar. Hydropower, if you have the chance to be in a country with a lot of hydropower, it's also a very good solution. But wind and solar are intermittent energy. As you can see, the capacity factor of wind is 1/3, solar is even lower, 1/4, and to cope with this intermittent source of energy, there is a need of base load. And nuclear, with the actual performance of nuclear, it's more than 90% of capacity factor, which is very high. And that's why we have some modeling tools, and when we do energy mix modeling, as I said, if you don't have hydropower, you have no chance to get to net zero if you don't have a component of nuclear power. Okay, so next slide. Yes, also there are other kind of analysis indicators that we look at, and one of them is the energy return on investment. So it takes into account a lot of things into this indicator, including the energy that is needed to produce the raw raw energy, raw material, and in particular, for example, for nuclear, well, you have to produce enriched uranium to feed a nuclear power reaction. But in fact, the way to enrich uranium is now it's using very low energy sources. So it's one of the best energy return on investment also. And one of the reasons also is that nuclear power plants, they have a lifetime of 60, 80 years. And so when you sum up everything on the lifetime, that's why you get such a good result. Next, I don't know, okay, I will go this way. So, nuclear power today. So we have also a lot of database in the agency. Nowadays there are 416 nuclear power reactors operating in 31 countries, and the installed capacity is 370 gigawatt. And it's not so much because it's less than 10% of world's electricity. Of course, it represents more in terms of low carbon electricity in the 1/4, but here we are speaking only about electricity. And one of the topic also is that it's not only decarbonization of the electricity mix that it needs to be achieved, but of the energy mix as a whole. And so regarding transport, industry, they are consumer of a lot of CO2 and a producer of a lot of CO2. And also we look at decarbonizing energy as a whole. Okay. If we look at the electricity production share from nuclear, you can see that about these 31 countries, so some are using a lot in the energy mix. So the first one is France. So as you can see, Slovakia, Hungary, Belgium, Slovenia. So many countries, in fact, in Europe have a quite huge factor of nuclear electricity in their mix. Okay, let's go. And if we look at the prospects, 59 nuclear reactors are under construction in the world. And we have a program in the agency, I will come back to that, for newcomer countries. And we have approximately 30 countries in the world that are interested in building this nuclear power plant that are new to this. So it's Poland is being part of the 30, so it's there are more and more interest, I would say, in the world for these nuclear power prospects. Okay. When we do some projections, taking into account, yes, the energy mix, the time it needs for a nuclear power program to go out of the field and so on. In the IAEA, we have our projection increase every year a little bit. So now, last year, we estimated that it would go to 890 gigawatts in 2040, which means that more than doubling, it's 2.2 or 2.3, doubling the existing capacity. And in the last COP in the Emirates, there were 25 countries that also signed paper to how to triple nuclear energy by 2050. So they go even over our evaluation, but it's more in an aspirational goal to triple nuclear energy. And I can tell you that in the 27 years in front of us, it's really a challenge to triple the capacity of nuclear energy in such a short time, because, yes, as I said, it's quite, for newcomer countries, it's quite a long time to have this nuclear infrastructure in place, all the instruments, legal instruments, safety authorities, capacity building in place, but also nuclear industry needs a lot of resources, manufacturing capacities and so on to, well, for these plants. And I think that from someone going into this industry now, there is a really bright future because, yes, to triple the capacity, it means to multiply by 4 or 5 the existing nuclear new builds in the world. Because in the meantime, some of the older power plants will close. So really have in mind that it's the need to get to net zero in terms of nuclear power is huge, and that it needs to, that's, well, first, it's a bright future, but also there is a need of competencies not only up to 2050, but even after, because this power plant will run for 60, 80 years. So now, what is available in terms of technology to meet this challenge? So I will speak about what I'm doing in my division, mainly in the IAEA. So I have different sections. One is working on advanced reactor technology. And I will say some word about fusion also. Yes, it's time. So, and I think that I am not the best specialist in the room. I think that with many professors from the University of Physics and so on, you know this, and I hope that you already also are familiar with that. But what I wanted to say is first, water-cooled reactors. So this is what is best known in the world. This is what is now installed and being installed as large nuclear power plants because it's a mature technology. So you know there are two kinds of water-cooled reactors, boiling or pressurized water reactors, as you can see, boiling on the left and pressurized on the right part. So the coolant is water, so that's also one of the reasons why it's now so popular. But the outlet temperature is about let's say 300 degrees. And as it goes to, at least for pressurized water reactor, into a steam generator and then a turbine, the efficiency is about 35%. And the it's working also under high pressure. So it means that for the reactor pressure vessel, which is one of the safety barriers, it needs to be also constructed in such a way that it withstands this pressure. So there are also safety issues, material issues, and so on. And these water-cooled reactors, they operate in a thermal spectrum. So I will go back to that. In terms of fuel cycle, if we had only water-cooled reactor in the world, it's you cannot close the fuel cycle with only thermal spectrum reactors. So I hope that I don't say things that are yet. It's okay. Okay. But as I said, it's not only a problem of decarbonizing the electricity mix. It's also an issue of decarbonizing the industry needs, the overall energy mix. So we are looking more and more at reactor technologies for non-electrical application, meaning that on top of electricity generation, which remains very good use for nuclear power, there is a need for process heat from the industry. There is a need for hydrogen production. Hydrogen, which can be used as for example, long-distance transport, for train, for trucks, for long-distance transport. There is a need also in certain countries for desalination. We have more and more countries from Africa looking at reactor technology for just the purpose of desalinating the water. Also, we are looking at reactor technology in terms of integration with renewable, which is because during the intermittent period, how to adapt the production of a reactor of the nuclear power plant, and also at replacing aging fossil plants. is also how to reuse the site first, but also sometime even the turbine, and with to minimize, in fact, the cost of the new nuclear power programs. So there are plenty of new usage, I would say, that request different reactor technology than the PWR or BWR technologies. Another reason also to look at different technologies, yes, this is, sorry, a slide that is complementary to what I said, is there are studies about what would be the necessary output temperature to cope with the industry needs. And as you can see, for example, for steel making, it's a very high temperature that is needed. For, let's say, for example, for thermochemical hydrogen production, which is also, there are a lot of R&D in this field. The output temperature would be around 700 degrees. So as you can see, there is a need of the different reactor technologies. Now, to cope with that high temperature, one of the technology that is looked at is what we call the gas-cooled reactors. So using helium as a coolant, as a gas. And there are different types of these gas co-reactors under design. So it's quite a new technology. While one is now operating in China, there are different technologies. One is with this pebble, what we call pebble bed reactor with Cloizeaux fuel, you know. And others are more with graphite, graphite bars and graphite reactor cores. So as you can see on this picture, but you can find a lot more in the literature. There are different technologies. And the outlet is more than 700 degrees. The efficiency is higher, but still there is high pressure in this kind of reactors. And so also, yes, something has to be done here regarding the high pressure. And these reactors can work both in the thermal and fast spectrum. Something that also is really important for the new sustainability of nuclear power is the fuel cycle. And one of the, there are different options regarding spent fuel and waste management. So one of the most popular fuel cycle is what we call the open fuel cycle, meaning that the spent fuel is being, when it is going out of the reactor and so on, so you separate all the different material, and then you go to disposal of used fuel. So that's what we call the open fuel cycle. And there are many countries dealing with this kind of open fuel cycle. And here, I would say, in the choice of the fuel cycle, there is a technology part, but also an economic part. If the uranium is cheap, the cost of reprocessing fuel or doing a closed fuel cycle with fast reactor is less interesting. But looking at technology point of view only, so there are two different other options. One is reprocessing of fuel, meaning that you can reuse the uranium and plutonium in MOX fuel, and so put that again into your reactors. And so the final waste disposal in terms of volume is less. And the last one is the closed fuel cycle, where it's also using a recycled fuel, but also there are some options to reuse minor actinides. So meaning that at the end, there is really the final waste disposal is really minimal. And when looking at these fast reactor technologies, so as I saw it, so it's quite complex. I mean that the nuclear industry shall be quite mature and to do this fast reactor fuel cycle. but it's looked at different countries. As I said, it's also an economic decision to be taken by the country, and depending on, as there are a lot of uranium sources, raw uranium mines around the world, prospects and so on. But in any case, about the different reactor technologies, so there is a sodium-cooled fast reactor technology that I'm also sure you know about. It's a mature technology. Some of these reactors have operated and are still into operation. But in the past, these reactors use and still use sodium. And you know, one of the, there are so many advantages for this sodium-cooled fast reactor, but really sodium as a coolant is difficult to handle. First, you need to have 3 different loops, not only 2 like in PWR, but 3. And yes, it can react very violently with water and air. So that's why some of these closed cycle options have not been pursued, especially in France. You know this, but there is a lot of knowledge gathered from this retired plants, but also ongoing plants. So nowadays there are new designers, new vendors looking at fast reactors, but using a different coolant. So it's either lead or lead bismuth in English, I think. And there are a lot of R&D in this field being performed to have, yes, the advantage of fast reactors coupled with less, a coolant that has less issues. But still, it's a new technology, and there are a lot of material issues or material R&D to be done before achieving a commercial reactor in this field. Okay, and last but not least, one of the reactor technologies that is also really, nowadays there are many different designs, is regarding molten salt reactors. So this is really a new technology. I mean, there are not many things in the literature, or there have been some, I think that one of the first reactor was a molten salt reactor a long time ago in the US, but it has not been pursued. And so there are a lot of R&D being done there. So of course, on safety aspect, it's very safe because the uranium is in the coolant, and so it's very intrinsically safe. The output temperature can be very high, good efficiency, and there's no pressure, so it's even less than the 0.2 megapascal. And still between thermal and fast spectrum. So, yeah. Overall, I would say that for somebody joining the nuclear field, being a young student as you, I think that there are so many reactor technologies that are reopened, that are so many projects that there is really a bright future. It's not only one way, it's also preparing the future. Yeah, because to face climate change, and in countries where there is a big grid, of course, large nuclear power plant, water-cooled, will remain the short-term option, but I can tell you that after there are so many different issues to solve that there is really a place for R&D. Also, we are speaking about size now. Large conventional reactors is a good option, but for countries with less, with a lower grid, smaller grid, I would say, or even for industry that wants to have also the production of energy close to where they are. There are these small modular reactors, SMRs, as you may know, and also even micro-reactors that are being pursued. So in the agency, we have a dedicated project in that. And among the advantage of reducing the size, okay, because one of the disadvantages is increasing the cost, but is that there are good advantages in reducing the size. The first one is that, yes, simplification by modularization and system integration mean that, for example, in some of the design, you can integrate a steam generator and the pressurizer for PWR inside the reactor vessel, meaning that so the risk of leakage, of loss of coolant and so on is really minimal in size. So in terms of compactness and so on, I think that there are very good advantages by reducing the size. Also because it is smaller, there can be kind of multi-module configuration, meaning that you can construct and operate even the reactors at different moments in time. Because it is smaller, you can also put part of your reactor building in the ground, so it's better on safety, on security aspects and even seismic aspects. And because the core is smaller, there are passive systems and passive safety. You can have more enhanced safety performance thanks to this passive system. So there are many advantages in terms of technology, in terms of safety, but also in terms of looking at how you will build your SMR power plant. In terms of economics, so large power plant is many billion of euro. I would say 8. Let's say 8 for one. But it's not an absolute numbers. But in terms of SMRs, you can, it depends on the size, but it's maybe 1-2 billion euro. And so it's a bit of affordability in terms of upfront capital costs. So when you are a newcomer country or smaller countries, I think that it's also something to be considered. In terms of economics, because it's by modular type and because it is smaller also, there is a scale effect that can be driven through serial production. If serial production is possible, and I will come back to that. And because it's modular, many things can be done in factory and be prepared in advance, so the construction time is shorter. One of the lessons learned from large reactor construction is that the biggest delay is during construction work at site. So flexible application with smaller reactors, there are remote regions, even floating nuclear power plants are considered for smaller footprints. So in terms of safety, but it needs a safety analysis, of course, but if the emergency planning zone stays inside the fence of the nuclear power plant, it's much easier also, not only for stakeholder engagement and but also for the emergency procedures and so on. As I said, yes, the size can correspond to existing coal fire plant, so easier to replace on a coal plant, to replace coal plants, and integration with renewable with smaller output. Also, it's something which is seen as more flexible as integration. So many advantages in that as SMRs, but still. And of course, it attracts a lot of development. So we have a database where we record all the SMR ongoing in the world in the IAEA. It's called ARIS. And this one comes from 2022. we are updating it just right now. So there were 80 designs, and I think that next time there will be even more. Some are, it's very different maturity. But you can see on this map the countries that are looking at developing the SMRs, the one that declare them to IAEA. Okay, so maybe it's not even exhaustive. So you see that there are many projects ongoing. And if we look in terms of maturity of design and in terms of output, so you can see a very wide range of designs. So under construction, operating, so you have a reactor in Russia, floating one. You have one now in China, and under construction China, Russia, and Argentina. But you see that more and more come to maturity. And some of them are considered also in different projects in Poland, as you can see. But the green part is water-cooled reactor, and you can see that many of them, the most mature, are in fact a water-cooled reactor, and the other technology come a little bit later. So, having said that, what are the takeaways before going to fusion? On fission power. So, as I said, nuclear has unique attributes to play a major role in transition to net zero. So, because of high capacity factor, low carbon electricity, and even energy that can be produced. It can complement renewable. It allows also security of supply. And it's one of the less risky pathway to net zero. As I said, it's also a bright future because it doesn't stop at what we know today. It's also linked with many other R&D and development ongoing. And so there is a need to quickly advance design and demonstration of advanced reactor technology, of these new technologies. And that's for this one, we will need a lot of competencies. Some word about fusion, because I am sure that also you are interested in what's going on fusion nowadays. So this is basic schematics, but you know that fusion is basically trying to reproduce what exists in the sun, is deuterium plus tritium going to helium plus neutron. So there is ongoing R&D in the fusion world for, I don't know, maybe 70 years now, something like that. But there have been quite number of new records those past years because there are more and more projects on fusion, national ones, but also private ones. I will come back to that. And the most promising technology is tokamak, using deuterium and tritium, because yes, and the physics, as you can see it, it is the most efficient in terms of energy produced, but there are also other program or R&D program that look at using also DD or D plus helium 3. Many, I would say, there is a renewed interest into fusion. There are also fusion different technologies. Tokamak is, as I said, the most popular one. There was a joint Torus for years that has been shut down. ITER under construction, but there is one now operating in Japan, and I think that China, Russia, and all those countries are also building tokamaks. Inertial confinement, laser confinement, is also looked at, and there have been a record in US 2 years. Well, a little bit less than 2 years ago, and electrostatic confinement is also looked at. And okay, I don't need to repeat the merit of fusion power. I think that you know that it's carbon-free, that because there is no long life radioactive waste production, so it's in terms of waste management, it's very good. It's inherently safe and reliable in unlimited fuel, but of course, will it work one day, and even if the reaction itself in terms of R&D is positive and the factor 10 or whatever, will the science in terms of material, in terms of, I don't know, magnetics, in terms of, will it be able to have a sustainable reaction that permits to go and, enough economical, viable material used and so on to have it economic and in competition with fission power. We believe that it's not for tomorrow, but still we are in the agency looking at really what's going on in the world nowadays, because there is, because of this climate change emergency and so on, there is a high public consciousness, and the new thing is that there are a lot of private investment now in fusion, more than $6 billion invested. More than 43 startups are working, not only as a technology itself, but some are working on the technology, supporting the technology used to that is needed, in fact, to go to commercial fusion. And so, yeah, we are also looking at that. There are two worlds. One is public world with a large international program like ITER or national program, private also, which is claiming that they will do fusion power for tomorrow. And in the IAEA, we are working with both to see and to try to develop together a roadmap to fusion power. So I would say that it's not only fission, but it's also fusion that have a lot of interest. And even if fission is a short-term answer, or a medium-term answer with generation 4 technologies, think that fusion is still valuable. And whatever you have acquired as experience in the fission world can be also translated into the fusion world later. So, having said that, now last part, what we do in the IAEA. So the statute of the IAEA is to accelerate and enlarge the contribution of atomic energy to peace, health, and prosperity throughout the world. And on that, so I think that you all know our DG, Rafael Grossi, but we work on different types of topics into the agency. So I'm part of the nuclear energy, where is it? Oh, okay. Of the nuclear energy department, but I have colleagues working in the nuclear science and applications. It's all which is not non-electrical, non-power application, I would say, medical, science, and food, agriculture, everything. One of the important also departments is nuclear safety and security. They do safety standards and safety guidance, and they help national regulators also in their capacity building or safety assessment. Safeguards is an important also department. I think it's even the biggest one in terms of number of people. We are 2,500 staff members in the agency, and safeguards is more than 900 of them. They are doing inspection in different countries, looking at nuclear material in those countries and monitoring, in fact, nuclear materials. And as a support organization, we have technical cooperation, which is in charge of matching the needs of developing countries with contribution from developed countries, and to organize as a project management organization this transfer of knowledge, and last but not least, management department to support us. So in the nuclear energy department, in my division, we are working for operators, because one of the, I should have maybe have started with that, but one of the most easiest way, in fact, to have low carbon electricity is to prolong the lifetime of existing power plants. So we work a lot with all the operators in the world on long-term operation, maintenance, outage management. We work also with them on innovation to ease the life management and even the performance of the plants themselves. We work with newcomer countries, and that's what this week the team of experts is doing in the Ministry of Climate now for 11 days. If we look at Poland, we say, so we are now at, does it work or not? Yeah, okay, yeah, it works. So we say that Poland here is now here, milestone 2. So Poland is under negotiation of contract for the first nuclear power plant, and we assess, in fact, the readiness of nuclear infrastructure at the end of phase 2. And we assess it against what we call the milestones approach, and we look at 19 different infrastructure issues. So we don't look at the nuclear plant itself or the program of the itself. Of course, it's an important part, but we look at national position. Is there a national organization in charge of the program? Is there a regulatory authority? Is there consideration about management system, funding, financing, all the legal and regulatory instruments, are they in place? Radiation protection, also the grid. Very important, human resource development, capacity building, and all you can see all the different topics which are here, including waste management and nuclear fuel cycle, as you can see, and also industrial involvement and procurement. So we have in our methodology defined different criteria corresponding to the different phases, 1 or 2 or 3, 1, 2 or 3, and it's not invented by IAEA. In fact, we have built this on more than 20 years of lessons learned from the different countries we work with, and we have built this methodology together. So at the end of the next week, so there will be some assessment. We do recommendation and suggestion. It's not mandatory or whatever. We are not here. We are here to support, not to give some. Yes, and so at the end of the next 2 weeks, so there will be some recommendation. But I think that this mission is well prepared on the Polish side. And it starts, by the way, by a self-evaluation by the country itself, according to this criteria. So it's done in a very transparent manner. So that's what we are doing in my division. As I said, we have conducted already 36 in-year missions of this type in, I think, I can't remember how many countries, but more than 20 plus countries. And we are working with 27 newcomer countries, as you can see, in the world. And there are a lot more also that will enter, that have some interest considering, and that will enter into this program. Also, what we do in my division, as I said, we work on SMRs, and we have a dedicated platform to coordinate the activities inside the agency, but also to give support to member states. I see that, yes, time is running. On another division of my colleagues, they are working on research, reactor, education, and HAU removal. And they are working with the Maria reactor. For sure, there was a mission last year, I think, in Poland. And about the nuclear fuel cycle, so this division is working on front-end, back-end reprocessing, nuclear material, nuclear fuel itself. They are also working on radioactive waste management, which is an important part, in fact, in when you enter into a nuclear power program. And decommissioning, environmental remediation. Yeah, I think that because there are a lot of reactors that have been stopped in the past decades that have started a long time ago. And so now we are gathering more and more lessons learned from the commissioning of these nuclear power plants, and also about how to go to what we call environmental remediation. So, as you can see, 182 reactors have been shut down already, but only 21 have been decommissioned so far. So there's also a lot of lessons to be learned in this field. In the nuclear energy department, we are also tools and services regarding energy planning and system analysis with the different member states. Because in fact, it starts with this kind of analysis for a country. And we have a dedicated initiative for that, Atom for Net Zero. We work on capacity building. So we have a lot of online training tools, but also we have schools, nuclear knowledge management school, nuclear energy management school. And we have, I think, was the largest library in the world regarding nuclear information, I would say. And we record, in fact, all the publication, documentation, and so on that is produced on nuclear. It's very, I don't know if you know this INIS database, but it's a very powerful database. And we are working on an important field also, which is stakeholder engagement. Because, yes, you cannot really start a nuclear power program if the population is not involved, aware, involved, and also if they don't have the good understanding of what is nuclear power in a country. So we have different tools for that, and we also work with country for this stakeholder engagement. And last but not least, as our DG is very much in favor of gender equality, we have two initiatives that are dealing with that. The first one is the Marie Sklodowska-Curie Fellowship Program. It's for master degree students, women students. And there, this year we have awarded 200 scholarships. So it's during 3 years. We follow students during 3 years, with including between 6 months and 1 year of internship, which is possible to be done in different countries. And well, I speak a lot about nuclear power, nuclear energy, but it's also for all types of different, I would say, fields. It's also for nuclear medicine, safety, security, and also we now have people from nuclear law, so it's not only a technical background that is needed. Just to know, it's for application, usually it closes around the mid of September, and then the awards are before the end of the year. So I think that it will continue with somewhat 200 scholarships per year. And so it's a very good program. And the last one that we started last year is for women who have who are in the first part of their career, is to retain women in the nuclear. So it's called Lise Meitner program. It's shorter times, it's between 2 to 4 weeks of visits and also training on the field. There were two, and it's for smaller groups, and it's 15 young women. And there were 2 already cohorts in US and 1 last month, even 2 weeks ago, I think, in Korea. And there will be more in a different part. Oh, sorry. And last but not least, I spoke to that about that earlier today. I'm part of Women in Nuclear group. It's a global group. There are, I think, I do not have the numbers, but it's something like 140 chapters in the world, so countries, and more than 35,000 women in part of this group. And well, I was part of this in France and now in IAEA. And I think it's good to network. It's open to men also, even if the name can be misleading. And I wanted also to promote the chapter of Poland, which is Women in Nuclear Polska. You will have this in contact in your in the slides, because yes, when you start a nuclear power program, I think it's such an opportunity to build a strong network in. It's to go to schools, because it's not only a problem of problem of attracting women in nuclear. Is start with attracting women in technical field. So it starts with going to schools and even and then higher degree. It's also how to encourage and retain women and to promote also their careers. Having said that, oh yes, I think that it's now time. Thank you very much. I spoke many, maybe too much, but I'm happy to listen to any of your questions.
Thanks a lot. So I think we will ask a few questions. The first one is already here.
Which disposal of nuclear waste is the safest?
Can you
Which method of disposal of nuclear waste is the safest? This is my question.
I don't think it's a question of safety itself, but it's a question of long-term commitment. So it's a question of volume of waste, and also, yes, as I said, long-term commitment, because there will still be ultimately some waste. But of course, the lower the volume is, the easier it is to monitor it over time, I would say. But it's really a question of economics, of commitment, of stakeholder also engagement. What is the population more in favor of also? And it's very technical, so some people, it takes time to explain the different options and to make the right decision also on a national level. Yes?
Thank you very much. Thank you very much for answering.
Yeah.
Thank you. It was very interesting presentation. So I have one question, which was, can you summarize it? The most modern solution is this small modular reactors and high temperature reactors. Can you tell in which country it is just really working, not only as research?
SMRs, as I said, it's in Russia and in China. It's working, but in fact, the SMRs, when it started the reactor development 60 years ago, it was small. They were building small reactors, maybe 300, 600 megawatt, and they enlarged the size because of the economic factor. Because also the safety requirements went higher and higher with time because of lessons learned, feedback of experience from the accident and so on. So in order to cope with more and more safety requirements and features, to remain economic, the size has grown up. So that's why now we have these large reactors. And one of the, so I would say SMRs, it's not what is really new now is that it's not just downscaling big reactors, it's also all the R&D which is ongoing to have passive safety systems, but enhanced passive system from the technology itself, and using all the innovations that has been done in terms of material, in terms of I don't know, for example, INC system monitoring and so on. Maybe I shouldn't say so, but the less innovative the reactor is, the easiest, the shortest deployment time there will be. So nowadays, it's also a question of licensing of the reactor itself. So, for example, in US, there is one which is licensed and others are ongoing. There are also some license application in different countries regarding these reactors. So this is the first step, to get at least the design license, or to get good feedback or recommendations from safety authority to go further. And then after, it's a question also of financing investment. Who is ready to do the first of a kind? Because yes, the first of a kind will be more expensive than the other for sure. So who is ready to take the risk to do this first of a kind? You need a site, you need investors, you need someone to believe in it, and you need also financial support. And that's why there are programs in US, in UK, in France, in different parts of the world to help these developers to go to develop the first concept, then to go to basic engineering, and to give some confidence that the model will go further, the development will go further, and attract private investors also, public and private partnership. So I don't know if I answered your question, but some are, yes. And high temperature reactors, yes, for sure. I know the only one I know is in China. There is also one in Japan that has been built, I think, but it was just before Fukushima. But there are different nowadays programs for high gas temperature. But the only working now is in China, yes.
Is it possible to find this presentation in internet? And if it is, where I can find it?
Yeah, I think you can answer.
Maybe I can answer this question. Indeed, this presentation and presentations from all our lectures can be found in our website. Do you know this or not? I will write in a second here in the blackboard. So if you go to the sub-website of a given lecture and scroll to the bottom, there will be presentation and also video recording, and maybe some other notes depending on the lecture. So.
Yes, and you can find, if you type IAEA something, you will find a lot of information.
Thank you for a great lecture. I wanted to ask if there is any chance for thorium nuclear fuel to become a commercial fuel in the future. If yes, why? If not, also why? So, thank you.
So first of all, I'm not a specialist, okay, about thorium versus uranium. Yes, there were some, I mean, on the paper, but on the paper, there are a lot of things that are possible. But on the paper, yes, thorium has many advantages. I think that to go to thorium, well, for example, uranium builds on a fuel cycle industry that has many decades of years of experience and so on. And you have to have a supply chain. So for the time being, thorium supply chain does not exist. So now I think that it is considered thorium as something that can be combined with uranium into existing fuel types or into fuel supply chain, and not to develop a thorium supply chain in itself from scratch, but to use it more as a complement to uranium and to see the benefit of it. But I'm really not a specialist. I think that we had recently published technical documentation on thorium, the use of thorium, that you can access also, maybe last year. That's a good question.
Is the IAEA considering if nuclear fusion reactors such as the one developed in Helion, so sort of alternative technologies such as a pulsed fusion reactor?
Which one?
Pulsed fusion reactor.
But you mentioned something?
it is developed in Helion. It's a country. Well, oh my God. It's a company based in the USA.
Yeah, okay. Helion, but there are also different other types of private companies that are building, in fact, fusion reactors nowadays in US. There are also in UK quite a large program of building facilities. As I said, Japan is also nowadays operating, but private companies, and China and Russia, and they are building other facilities. But you can see, as we have a database where we have all these fusion facilities. I think it's more than 150 now in the world. So do we consider, we have not the clue, we have not a crystal ball, I would say, in the agency, but we really want to follow what they are doing. And as an international agency, we believe also that one thing that I didn't mention is about harmonization and standardization. One of the difficulty, for example, for SMR, serial production and so on, is to get the same requirement in the same in different countries, in different parts of the world. But it's there are different licensing processes. There are different codes and standards being applied. There are different requirements. Even if the safety standards of the IAEA apply to every facilities, and but it's very high level. But the more you come into the detailed part, the more differences you have and gaps you have between different countries. And in the fusion field, why we want to work also not to wait for the commercial fusion of the first one to be on the market, is because we believe that if we harmonize and standardize from the beginning, it will be easier for the deployment itself. Because of course the safety regulation, we always apply a graded approach, and so fusion facilities, the safety level will be different from fission. So we want also to accompany this movement towards this to facilitate deployment of commercial fusion in the future. But well, I cannot tell you what is in the future. I'm sorry.
Thank you very much for answering.
Thank you very much for your interesting presentation. I want to ask you, from your point of view, what is the main factor that is paralyzing the development of SMRs and MMRs in Europe?
In Europe itself? In the world, yeah. Yes. I think that to develop a reactor, you need really experts. You need experts having knowledge in thermohydraulic, neutronics, having the tools to do it, having even the experimental access to experimental facilities to demonstrate the safety of the reactor. Because, as I said, it's not only a paper reactor. At the end of the day, you will have to demonstrate the safety of the reactor. And so it's the SMR vendors are mainly in operating countries, countries where you have developers of reactors, large ones. It started with that. And nowadays we see more and more startups, but it's more often it's people with this kind of competencies that have worked for many years in the nuclear industry that decide to go to do this type of to develop this type of startup. And what I think is very good nowadays is that they are, because of the innovation programs that are either national or regional, and because of this sharing of knowledge between national laboratories, because they also have a lot of experience in that. this dialogue and the support that they can bring also to the startups is essential. And I see that it is a movement ongoing. I was last month in Brussels, so we had this nuclear energy summit in Brussels, but also the day after there was this announcement of the SMR Industrial Alliance launched by the European Commission, supported by three Director General of the different commissions. And they are putting in place a program. They are not, in fact, they are managing the program itself, but it's a dialogue between vendors and regulatory authority, no, not regulatory authority, but more industry, more regarding waste, so they are working on transversal topics and helping vendors to have a common approach, I would say, in Europe. So I see more and more of this in Europe, but also internationally speaking, where it's facilitated, which was not the case a few years ago. And as it takes time to develop a nuclear reactor, to get it qualified and so on, licensed and qualified, I think that, yes, there will be results, but it's not immediate like this. It doesn't take 2 or 3 years. It takes a little bit more than that. But some are now in basic designs. Huh? Some are considering siting also in different countries. So it will come. Yeah, you're skeptical.
Okay, it seems there are no more questions, so we can thank. There is one more? Okay. I think you can.
Thank you again for answering my first question. What did we learn from the situations like Chernobyl? What did we learn and what mistakes were made?
Oh, I think that there are a lot of literature regarding the feedback, the lessons learned from Chernobyl, but there were a lot of different, in the safety culture, nuclear safety culture, there are a different kind of principle, safety barriers, safety things, and in the lessons learned from Chernobyl, that many of them, of the steps were overridden. I mean, they were not respected. So that's why also safety culture is based on different barriers. So also, for example, the 3 physical barriers in the nuclear reactor, but not only a redundant system on accident, also how to look at, to reduce the impact of accident. After Fukushima, a lot has been made also on emergency, how to deal with emergency crisis. Each time there is something, there is lessons learned, shared, and things that are put in place. And human factor was also very important in the case of Chernobyl. As in the safety culture, human factor says that yes, if there is a doubt, yes, first of all, you have to follow the procedure. You have to follow the rules. So this is the first thing. But also, if you see something going wrong or whatever, you have to raise your hand. And I think that it is important, and that's why also I like to work in this field, because you are in a field where it's quite transparent. For example, for operating power plant, it's quite competitive world, but still there is a lot of exchange between operators, because from this exchange, lessons and so on, that's where it's improving safety of reactors all over the world. And everyone knows that if there is a problem somewhere, it will affect all the nuclear industry, all the either operating or future plants. And that's something where I think that it's a strong point, in fact, this over exchange and transparency.
Thank you so much for this answer. Thank you, and this was my last question.
Okay, well, I see some new hands. I'm not sure how much.
Yeah.
Let's.
I guess
Sorry, please use the microphone because not
Yeah.
everyone.
What I'm going to ask probably is something which is obvious to most people who are in this area. But I was just wondering, I know that in France, and you represent the France, there is more than 70 units,
Yeah.
or you come from France,
Yes,
there's more than
go.
70 units operating in this nuclear plant, providing more than 70% of the capacity. In Poland, we consider the first unit or maybe couple of units which will be in one place, and then the program will go to other areas, possibly Bełchatów area, to replace phasing out in 20-something years Bełchatów power station, which is the biggest base load provider in Poland. I was wondering if the fact that in France you have small units, it's more economic, or it's because it was built in the 70s, and now it's more common to have the bigger units which provide the scale, the lower costs, or what's the logic behind it? That's my one question. And the other is that you have mentioned that it works very well with renewable energy sources, and we know that wind and solar, they produce when they produce, and when they produce there is usually a lot of energy in the system, and there is so-called overflow, so other producers sometimes switch, or they actually have to be switched to stop producing. And how that works with nuclear, does it mean that the nuclear power stations have the flexibility of production, or because like in case of coal-fired, to stop the unit, it takes a long time to repower it, more than a month, so they cannot stop, basically. Is it more flexible with nuclear, and they can sort of reduce how much they produce to allow renewables to produce, or how that sort of union works?
So
because I don't quite know.
first of all, in France there are there's 56 reactors operating, but it's a large one. The smallest one is 1,000 megawatt. So and there is a series effect. So there are many reactors of the same type, which is good for on an economic point of view. And I would say that when you are in a country where there's 70, well, I think now it's 67% of nuclear electricity, but there is also hydropower in France. The renewable is still quite small in the grid, and it will increase. And so regarding the flexibility of the reactor, yes, it's quite flexible. I cannot remember, but it's quite flexible. And one of the I didn't touch about that, but the economic factor also that is being considered for investment of nuclear. Nuclear is, of course, will it be? Will I be able to sell my electricity on the market later on? Because I see in countries where, for example, Finland, where now they have this big reactor OL3 working. Before it was commissioned, the prices were very, very high because and very fluctuating. It was from 0 to, I don't know, very high. And this, as a big reactor, has allowed to stabilize the prices. But of course, when they have to shut down for maintenance, it starts again with the fluctuating. So, but obviously in developed countries, the grids are interconnected. So, meaning that it's also a regulation possible on not only national but international, regional point of view, I would say. And the fact that SMRs are of smaller size, I think will also help. That's what we are looking at, what we call integrated energy systems. We are looking at how to switch from one to the other. And also how to cope with production of, for example, hydrogen, to switch from electricity to hydrogen, to store some part of it. And so we have tools that are doing this kind of analysis. Yeah. But I don't completely answer to your questions. But yes, it's very flexible. Yes. It's not known, it's quite flexible. Of course, the operators, they prefer to have stable operation and so on, but it's...
Yeah. Okay, I see one more or two more questions. So let's make this really the last two, because we in fact cannot stay that much longer, but let's make this the last two questions, 1 and 2.
Does the IAEA control in or monitor in any means the nuclear startups in terms of safety or like legality?
No, we advise, we support national member states. So, for example, my colleagues in nuclear safety and security department, they work with national regulators to support them. But it's really, yeah, maybe I should have started by that, but nuclear energy, nuclear power is something which is a national decision, a sovereign decision. We call it sovereign decision, meaning that, yes, we are there to support, but not to take any decision for a specific country. And so regarding, do we look at vendors and so on? Some vendors, they come to see us because we provide also advisory services to them. But it's just advices. It's not nothing compared to going to a regulatory authority and get a license.
Okay, so thank you for your presentation, first of all. My question is, all your reactors on your presentation was for a generation reactor family, yes? And there are any plans from the scientists or engineering to try to develop the new generation of the reactors, for example, 4+ or 5, or just focusing on the fusion? Thank you.
Yes, what we call generation 4 is what I showed, high gas temperature, molten salt reactors, and fast reactors, either sodium or lead fast reactors. So I don't know. So we are working with the developers, yes, on that. We are providing tools also. I didn't say so, but we have simulation tools that maybe you use also, on-core tools and so on. Because for yes, for training, it's quite not popular, but it's, at least it's an open tool. And we provide this kind of support. And for fusion, we are more working with, in terms of coordinated research project, for example, with scientists. We are also some conferences for fusion. There was one last year in London. It's one of the most popular conferences in the world of fusion. And this year, in end of October, we have the first SMR conference in the agency. So it's in Vienna, not far from Poland. I don't know if there is some opportunity to come. But yes, we really, one of the role of the agency is to gather people and to discuss and to help people and countries make informed decisions. See?
Okay, thank you for the great lecture and the great discussion.
Okay, thank you very much. Have a good evening.